Okay,
So, so hello everyone. Thank you very much for being here. It's the last meeting of the year. Today I have the honor to introduce Shlomo Gelaki from Iowa State University. He's going to talk about twisting of affine algebraic groups. Thank you, Shlomo.
Yeah, so thank you very much for the invitation. I wish I could say that I'm happy to be again in Cordova, but maybe some other time. So yeah, so I want to talk about twisting. So let me start maybe with the main motivating problem, which is fiber functors on rep G. So G will denote an algebraic group, let's say over the complex numbers, although there have some results in positive characteristics, but for simplicity. And let O of G denote the coordinate algebra of G. So just recall that so O of G is a commutative Hopf algebra, let's say finitely generated even. So we'll denote by C the category of co-representations of O of G. So always finite dimensional. So finite dimensional co-modules. And this is the same as the category of representations of G. So again, finite dimensional rational representations. And so I'm just recalling stuff that you probably already know, but let's just recall that C has a canonical structure of a symmetric tensor category, such that the forgetful functor equipped with the standard tensor structure is a fiber functor. So fiber functor in this talk will always be tensor functor to begin with, and exact, fully faithful. Okay. All right, so the main problem, general problem, is to classify fiber functors up to equivalence. So let's just recall that fiber functor, so you have a functor F, which is, as I said, tensor exact, fully faithful, but it is equipped with a tensor structure. So we have this standard one, or canonical one if you wish, but there are, in principle, other tensor structures, and even other functors, as abelian functors. So in fact, this is I would say pretty much an open problem still. So let me try to briefly explain why. So in principle, there are two types of fiber functors. So standard ones are those which preserve the dimensions of the representations as vector spaces. But this need not be the case. So there are non-standard fiber functors. Namely, you can have fiber functors which do not preserve dimensions. So clearly this is much harder, and very little is known about non-standard. So let's start with standard. So for example, every fiber functor is standard if G is a finite group. And for example, if G is solvable algebraic group, so I mean, for finite groups, I mean, every fiber functor in a finite tensor category preserves dimensions automatically. So, but for algebraic groups, this is not the case. But for solvable, let's say connected solvable for simplicity, since all irreducible representations are one-dimensional, it must preserve the dimension. Okay, because simple objects are invertible, so then it has to be the case. But for example, so so this is a well-known theorem that standard fiber functors means that as an abelian category, the functor can be identified with the forgetful functor. So you just send the finite dimensional representation to the underlying vector space. Okay, and then standard fiber functors therefore are in bijection with tensor structures J on the forgetful functor. So at least as an abelian functor, it is just a forgetful. And then there is just the question of what are all possible tensor structures. Okay. But for non-standard, you don't even know what is the functor on the level of abelian functors. Okay, that's why it is much harder. Okay. So at any rate, let me just mention there are non-standard fiber functors, for example, already for SL2C. So there is a paper by Bichon in which he classifies all fiber functors. And in particular, you can send the two-dimensional vector representation to vector space of arbitrary dimension in principle. Okay, so to sum up, I mean, since I'm not going to talk about, the problem is really hard and very interesting, and non-standard is unknown. Standard should be a little bit easier, but still very much open, but I'm going to talk about cases where we know. Okay. Okay, so since now we are interested in tensor structures on the forgetful functor, then easy reconstruction argument shows that they are in bijection with certain elements in the second tensor of the Hopf algebra. So these are Hopf-2 cocycles. So let me briefly recall. So what are Hopf-2 cocycles for G? So G is still an algebraic group. So these are, I remind you, invertible elements, J, going from OG tensor OG to C, and they satisfy this 2 cocycle condition. Let's call it, okay? And for some reason, the keyboard now is not working. So anyway, so I'm going to scroll. The idea was to introduce.
Maybe if you click on the PDF.
On the PDF.
Yeah, just click on the PDF and then try to use the keyboard. Anywhere in any page, like there, where I can see your cursor.
Great. Thank you very much. Now it worked.
Okay.
Thank you. So yeah, so as I said, so any Hopf-2 cocycle defines a new Hopf algebra structure, which is denoted by that, on the same co-algebra, O of G, and the new product rule is given by this formula. So it's essentially conjugation by this invertible element. Okay, and this is an associative product, and twisting the multiplication in O of G does not change the representation category, namely C, which is our rep G, is equivalent to the co-representation category of this new Hopf algebra. Okay, so equivalently, that's what we mean by saying that J, which is now a Hopf-2 cocycle, it defines a tensor structure on the forgetful functor. Okay, and this reconstruction theorem is, so you have this tensor structure, you can reconstruct from it a Hopf-Suckow cycle, and a Hopf-Suckow cycle gives you a tensor structure on C. Okay? So, therefore, the theorem is that Hopf-Suckow cycles for G are in bijection with tensor structures on the forgetful functor, and thus with standard fiber functors. Okay, so that's the problem of classifying standard fiber functors is equivalent to the problem of the following problem. Classify gauge equivalence classes of Hopf-Suckow cycles for G. So I didn't mention before gauge equivalence, but you know that Suckow cycles may be equivalent in some sense, and they provide the same tensor structure and so on. So if I forget to mention, whenever there is classification, it should be gauge equivalent. So we are talking about equivalence classes. So this is just a translation. So standard fiber functors, we need to understand Hopf-Suckow cycles for G. Okay, so for that, let's introduce the following. So given a Hopf-Suckow cycle, J, you can construct this element. So star is a convolution product. Okay, so J to 1 inverse times J. And this is a new, so this defines an R matrix or cotriangular structure on this twisted Hopf algebra. And let us say that J is minimal if this form is non-degenerate. So for example, the standard one, of course, corresponds to J equals 1. So it is not minimal unless G is the trivial group. All right. So the theorem says the following. So first of all, and this is, I mean, I wrote here my paper from 15, but this was realized for finite groups many years ago by Movshev and Ettinghoff and myself. But at any rate, it holds in general. So there exists a unique up to conjugation closed subgroup H and the minimal Hopf-Suckow cycle J prime for H such that J is gauge equivalent to J prime. So in other words, since we are interested in gauge equivalence classes, every Hopf-Suckow cycle for G comes from a unique up to conjugation subgroup for which it is minimal. Okay, so we are going to call H the support, or if you wish, again, the equivalence class of H under conjugation. This is the support of G. So every Hopf-Suckow cycle for G is supported on some closed subgroup. Okay, and therefore, therefore the problem of classifying standard fiber functors is equivalent. Oops, sorry, sorry, I already said that. So therefore it suffices to classify in principle pairs such that J is minimal for H. So if you are interested, I don't know, in finite groups, unipotent groups, reductive groups, whatever, it is enough to find, to classify all subgroups and their minimal Hopf-Suckow cycles. Now, of course, not every subgroup has a minimal one, but all right. So let me start with something just to give some examples. So I'll do now, let me review what happens for commutative algebraic groups and then finite groups, which motivated everything, and then move on. So for example, so Hopf-2 cocycles for commutative algebraic groups. Now, before I start, what is nice about in the commutative case is that Hopf-2 cocycles form a group. So in general, if you have two Hopf-2 cocycles, their product may not be a Hopf-2 cocycle. But in the commutative case, it is. So therefore, we get a group which is known for other reasons, which I will mention. So let A be a commutative, a fine algebraic group. All right. So let us write A as, you know, direct product of the reductive part and the unipotent part. The reductive part is a torus, direct product with some finite abelian group. Okay, so T is a torus, and the unipotent part is, you know, an additive group. All right. So for finite group, you can look at the character group. And so the character group of T is just ZK, and so on and so forth. Now let AU be the Lie algebras of A and its unipotent part. So let me just go over this theorem. This is with Etinghoff. So as I mentioned, you see H2 inv. So this is so that denotes the group of equivalence classes of Hopf-2 cocycles. So in the abelian case, they form a group. Okay. And invariant, because you can consider for arbitrary G, you can consider all Hopf-2 cocycles such that the twisted Hopf algebra that I talked about before, OG twisted by J, is the same as OG as an algebra. So namely, the multiplication is invariant under J. Okay, so in the reductive case, for example, we just know that all Hopf-2 cocycles are just alternating pi characters, okay, as groups. And minimal correspond to non-degenerate. In the abelian, in the commutative unipotent case, you see this group is just wedge 2 of the Lie algebra of U, and there is an explicit formula. This is a special case of so-called universal quantization function. Okay, so start with any R, take the exponent, you'll get Hopf-2 cocycle. And again, minimal correspond to non-degenerate. So in general, therefore, so for every abelian A, you have this group isomorphism. Okay, so in fact, I didn't write it here. Let me just mention that in this paper, Etinghoff and myself, so actually we have a description of H2 inv G for any connected algebraic group. So for any connected algebraic group, the second invariant cohomology turns out to be an abelian group. And we have a description of it, but here I just wrote it for commutative groups. Okay, now before I get to the finite group case, let me go ahead just and mention that I mean, a finite group with a minimal Hopf-2 cycle must have a square order. We'll see why. But already here, you see that even in the commutative case, this is not the case. So for example, the dimension of a torus with a minimal Hopf-2 cycle may not be even. It can be odd. So here is an example, just, I mean, the point is that so as I explained, if T is GM cubed, so we need to, so Hopf-2 cycle correspond to alternating bicharacters B. Okay, so that's how it looks. And this is going to be non-degenerate if A, B, and C are generic. So there are plenty of minimal Hopf-2 cycle for three-dimensional torus. So it doesn't have to be. So you see already something which is different from the finite group. So yeah, so this is a good point to recall what happens for finite groups. So Hopf-2 cycles for finite groups. So G is a finite group now. So theorem, Movshev, and Ettinghoff and myself. So gauge equivalence classes of Hopf-2 cycles for G are in bijection with equivalence classes of pairs. So H is a group of central type. Doesn't matter. In particular, it has to be solvable. And as I said, its order has to be a full square. And this is the support, okay? And W is a certain class of 2 cocycles. It has to be non-degenerate in some sense. Okay, so the main point, since I don't want to talk much about it, I mean, you see it follows the plan I mentioned before. So you have to classify finite groups with minimal Hopf-2 cycles, and such, first of all, have to be groups of central type. And the Hopf-2 cycle corresponds to something more familiar, which is a non-degenerate 2 cycle. So that's the situation. And now a key role in the work of Movshev and ourselves is to consider the one-sided twisted algebras, COGJ. That's not a Hopf algebra in general. So far, Hopf-2 cycles had to do with new Hopf algebras, but they also provide new algebras which are important, and it's simple quotient. So the point in Movshev is that H, which is the support of J, gives rise to this twisted algebra, which is simple, namely a matrix algebra. Okay, and this is a key, because once, I will explain later, but you have this simple algebra, which is a matrix algebra with an action of G, or with an action of H, say, and that gives you a 2 cocycle, because it's a matrix algebra. Okay, so that suggests that if you want to classify Hopf-2 cocycles for algebraic groups, maybe you should consider these twisted algebras. Maybe when you take the support, it's a simple algebra, and maybe if it is a simple algebra, you can produce from it something which is more familiar, like 2 cocycle or something. All right? Okay, so let's now discuss a bit this algebra. So this algebra, OGJ, twisted on the right function algebra of G. So this is the unital associative algebra with product rule. See, it's half, just the right half of the product rule of the Hopf algebra. In the Hopf algebra, we also had here J inverse A1, B1, and so on. Okay, so it turns out that this is a unital associative algebra, and more, in fact, moreover, it is a torsor G algebra. What does that mean? So it is equipped with a G action, just by left translation, such that as G modules, it is nothing but the regular representation of G. So G acts like it acts on OG by left translation. Okay, so now let H be the support of J. So we can look at functions on G mod H. H is not necessarily normal, so this is just cosets. In other words, right invariant, H invariant functions. So it turns out this is a subalgebra also of the twisted one, and in fact it is in the center. It is a central subalgebra. And this is because OGH is a left coideal subalgebra, so if you look at the product rule, it follows. So let Z denote the center of OGJ. Okay, so we already know that it contains right H invariant functions. So Z is a commutative algebra with a G action, because G acts on the whole algebra. So its spectrum is an affine scheme with a G action. So the first main property of these algebras is the following. So they are finitely generated, but the center is precisely this. So the center of OGJ identifies the support. So it's exactly the support invariant functions. So in particular, what do we see here? That if J is minimal, then the center of this algebra is trivial. And if G mod H is affine, then the converse holds too. So let me give you an example, which I'll use later. So if G mod H is not affine, say projective, for example, then the center may be trivial and the algebra may not be simple. So for example, if you take G to be SL2C, and you take H to be a Borel subgroup, and then the Lie algebra of H is spanned by two elements, big X and big Y, and the commutator is this one. So this is the unique up to isomorphism non-commutative two-dimensional Lie algebra. So you can define an element J using the following formula, and it defines a minimal Hopf-Tuchel cycle for H. Therefore, a non-minimal for G, because remember, the twisted Hopf algebra OG surjects onto the twisted Hopf algebra of OH with the same J, because J is supported on H. So it cannot be simple because it has a quotient. Okay, now let me just say one quick word. What do I mean by this J? So one should think of, you should think of J as a collection of linear isomorphism from V tensor W to V tensor W. over all finite dimensional representations of G, V and W. And it is well defined and it is functorial, so it gives rise to an element. Okay, because I said that J is, is a linear form on OG, tensor OG, and one has to understand how to get a linear form. But at any rate, you see the point here is that, of course, G mod H is not affine, but rather projective. So if you twist the function algebra of SL2C from the right by this J, you will get an algebra with a trivial center, but it is not simple. Okay. So but for example, in the for finite groups, as I mentioned before, it works. It's equivalent. Saying that OHJ is as a trivial center is equivalent to saying that J is minimal. Okay, so let's see what happens. So I'm continuing with Movshev theory. So let's see for tori. So Movshev theory is, let me just say it again, is what happens to the one twisted from one side function algebra, and in particular, what happens if J is minimal? Is the one-sided twisted algebra simple? And if yes, what can you do with it? All right. So for tori, it's going to be, let me quickly go over it. So T is an algebraic torus of dimension K. T hat its character group as before. So let S be the support. So we know what that means for, and L its dimension. So one thing to note is that, so you start with connected, T is connected, but the support may not be connected. So again, this is one of the issues in the algebraic case. So let S not be the identity component of S. So fix a splitting, and so then you can embed its function algebra inside O of T. So assuming now I have a Hopf-2 cocycle on T, so we have this R form. Okay, so yeah, maybe I should have said that. So take generators x1 to xk for the character group. Okay. So at any rate, so you have some numbers here. So the point is the following. So you see, you get here some familiar things. So when you have a k by k matrix of invertible numbers here, lambda ij, lambda ii is of course 1. So if you can look at the algebra generated by x1, xk, together with their inverses, subject to these relations. So this is a well-known algebra coming from a torus. So for example, it is known that it is simple if and only if the center is trivial. So that sounds similar to something we saw before. So indeed, let me just state the following theorem. So if you twist O of T from the right, so this is a well-known creature, this E of lambda. So in particular, it is an Noetherian domain with this center. So S is the support. So as in the previous theorem, the center so the quotient is affine, so the center should be functions on T mod S, and this is the case here. But more precisely, we see exactly what is the algebra. So let's skip the description of S. So let's see, in general, you see that now I'm looking at, I'm twisting O of S. So J is the support of S. And this is indeed a simple algebra, like in the finite case. And it looks like a twisted group algebra of the character group. Or if you wish, some cross product algebra, doesn't matter. But the point is that for tau I, if J is minimal for S, then the twisted algebra is indeed simple. Okay? But of course, unlike the finite case, when it was a matrix algebra, which is very simple, it's not a matrix algebra, but anyway, this is still, it still holds. So let me move on now to unipotent groups and see what we can say. So G is going to be now unipotent, so it's automatically connected, no problems with over C. Let's say the dimension is M. So let me remind that in this case, O of G is a finely generated, commutative, irreducible, pointed Hopf algebra. And as an algebra, it is well known that it is a polynomial algebra. Okay? So as an algebra, it is a polynomial, and there is some coproduct. So let W of n denote the Weil algebra of GK dimension 2n. N can be 0, but mostly bigger than 0. And now let J be a Hopf-Zucker cycle for G, and let H be its support. Okay, G is unipotent. So here is the main theorem about the structure of this one-sided. So we have an algebra isomorphism between the one-sided twisted as a tensor product of two algebras, Weil and the center. We already know. Also in this case, it is known that G mod H is affine. G is unipotent, so G mod H is affine, so this is the center. So in particular, again, OGJ is an affine Noetherian domain. So follows from here that H is the support, so you see that the dimension of the support has to be even. That's the analog of being squared in the finite case. So in the unipotent case, it is even, and the twisted is simple, and the simple algebras arising are Weil algebras. And then that requires more, but so you see, as I mentioned before, in the finite case, for finite groups, this OHJ was a matrix algebra with an action of H, isomorphic to the regular representation. And we know that this action corresponds to some two-cocycle. It's kind of projective representation. Okay? That was the omega. So now it's a Weil algebra. But since it is a Weil algebra, we can get now from it that in fact H admits a left invariant symplectic structure omega. So in other words, its Lie algebra is a well-known object. It is a quasi-Frobenius Lie algebra. So Frobenius Lie algebra means that this omega in H2 H star is a non-degenerate 2-cos cycle. It's a well-known object, which you know already, so it appears of course in Drinfeld work, in the classification of triangular Lie bialgebras and so on and so forth. So again, but this is harder to show, but at least it's in the same spirit. So the point is that this OHJ, as I said, is isomorphic to the regular representation of H. And since it is a Weil algebra, there is an action of the Lie algebra of H by derivations, but all derivations are inner, and that's how you get a 2-cos cycle, because it is inner, but then you have to show that this 2-cos cycle is, you know, non-degenerate and so on. So you have to show that it comes from some coadjoint orbit and use some rather classical stuff about here. But at any rate, you get from it, let me summarize here. So you see there are two, I'll comment about it later on. So equivalence classes of the following sets are in bijection one with each other. So Hopf 2-cos cycles for G. G is unipotent, I'm reminding. Pairs H omega, where H is a closed subgroup and omega is a left invariant symplectic form on H. 3 solutions are to the classical Young-Baxter equation. So what I want to say here, so you see Etinghoff-Jellaki 2008. So we proved it using the Etinghoff-Kashdan quantization theory. So we did more general stuff here, but at any rate, we had to use this machinery of Etinghoff-Kashdan. And what I said before is that once you know this theorem, then in fact it follows similarly to the finite group case in Morphev theory. So you don't need this machinery, you just, once it is simple, as I explained, you can, because the equivalence of 2 and 3, this is something that is well known by Drinfeld already. So 2 and 3 is really nothing new here. I mean, 1 and 2 is the new thing. So at any rate, so you see that for unipotent groups, it's very similar to the finite case. So, but the point is, I'm not going to say much about it. So combining this theorem and the classification of Hopf 2-cos cycles for tori that I mentioned before, plus something else, which is not trivial, we can get the classification of Hopf 2-cos cycles for any connected nilpotent algebraic group. So of course, the point being that connected nilpotent is direct product of tori and unipotent, but you have to somehow glue the two things. But at any rate, for connected nilpotent algebraic groups, they also correspond to solutions of the classical Young-Baxter equation. Okay, and before I continue, let me just say that this is the most general classification of Hopf-2 cocycles there is in the literature. So already for solvable, which are not nilpotent, the situation becomes much harder. And there is still no classification of Hopf-2 cocycles for solvable, let alone reductive. So the intuition somehow, so new ideas are needed. I mean, first of all, it is still unknown if, if J is supported on H, then you get something simple, let alone what type of simples. But even if it is simple, I'm not sure it is enough.
Shlomi, can solutions of the classical Yang-Baxter equation in an nilpotent group, nilpotent Lie algebra, can they be classified or is just a reduction?
They can be classified in some sense. Yeah, if you accept, classification for, in the unipotent case, so, the Lie algebra is unipotent, direct sum, something simple, abelian, and you can write down a decomposition of an element and say that it is a solution if and only if something. Yeah, that it appears in my paper. Yeah. So, yeah, so let me maybe, because I think the most important part of this talk should be the open questions, because they are missing some ideas, and I think it's very interesting and important. So what can we say about Morpheus theory for general groups? So let G be any affine algebraic groups, and J Hopf-2 cocycle with support H. So the question, is the algebra OAJ simple? What are the simple algebras which can be realized in this way? And there are many other questions. For example, is it Noetherian? You can ask a lot of things, but so I'm very interested in this problem. And so let me, for example, since we already saw it, let me just give you an example. So if H is this non-commutative two-dimensional, yeah. So the Lie algebra is the unique two-dimensional one. So before I wrote down this J, this is a minimal twist. So in this case, you can just compute that if the twisted one is, so WYX denotes Weil algebra with two generators. And you see, you have to localize, you have to add the inverse. And this is a simple algebra. This is the simple algebra of differential operators on Gn. But I don't know if this is always simple, if H is solvable. So this is just an example. So I'm sure all simple algebras are, familiar, but it's interesting to see exactly what you can get. Okay, so yeah, I'm not sure because of all of that. Well, what exactly is the time situation? Up to you, because
yeah, you have like 10 more minutes.
Yeah, it's okay with you?
Yeah.
Okay, so in the last 10 minutes, maybe I want to switch to, so once you, if you know the classification for J for some groups, say unipotent, you may now go back to the Hopf algebra. These Hopf algebras, they give the same category, but they are interesting as Hopf algebra. So for example, when G is finite, Etinghoff and myself many years ago studied the representation theory of these Hopf algebras. Okay, of course, we knew they are semi-simple, so it's much simpler. So let's discuss a bit the algebra structure for unipotent. So G is unipotent. Okay, everything can be extended to the connected nilpotent, as I said, but forget it. Okay, so now it's a Hopf algebra. So support is H, as before. G unipotent, J Hopf-Tukos cycle, support is H. So first thing is that it's an affine Noetherian domain with Gelfand-Kirillov dimension dim G. Nothing very surprising, but as I hinted in one of the questions, it's not clear they are Noetherian. I mean, they should be Noetherian in general, but I don't know. But anyway, here it follows. And in particular, one can look now, you know, on bi-invariant H functions on G. I denote it by, like that. So this is a central subalgebra. It's not the center, but it is central. Because remember that unlike when you twist from one side, when you twist from two sides, for example, if G is commutative, then the whole thing is commutative. You don't change anything. So for commutative G's to study this is not a new Hopf algebra. It's the same. But if G is unipotent, say non-commutative, this is a new Hopf algebra, and it contains this central subalgebra. And so let H denote the Lie algebra of H. So it's nilpotent. So first theorem is that, and this is also similar to the finite group case. If you consider this form Rj, so the R matrix, then it induces an algebra isomorphism. So H is the support. So if you twist the functions of the support, then in algebra, in fact, it's the universal enveloping algebra of H. In the finite case, it is just the group algebra of the minimal one. So in particular, you see that this Hopf algebra is a unique finite dimensional irreducible representation because H is nilpotent. So now in general, let's not go into too many details, but as you can expect, so J may not be minimal for G. So the Hopf algebra OGJ is a certain, cross product algebra between, this is just the universal enveloping algebra of H, as we saw before. And here, so this algebra, OGH can be twisted from the left by J. So instead of from the right, but it's not the same. So this is typically non-commutative. So at any rate, the point is that you have this description of the Hopf algebra as an algebra, but doesn't help much when it comes to representation theory. So let's see what can we do in order to describe irreducible, finite dimensional irreducible representations. So let me introduce these algebras. Let me explain what it is. So fix an element G in the group, and let's denote by Z sub G the double coset HGH. So the point is that it's an irreducible closed subset of G. It follows from the famous theorem of Constant and Rosenlicht. And again, we have to use unipotency here, because so a double coset is just an orbit of a left action of a unipotent algebraic group, H cross H on G. And orbits of actions by unipotent groups are closed. So as usual, let's H sub G be the intersection. I mean, H may not be normal. So the dimension of this irreducible set is given like that. And now let I of ZG be the defining ideal. So ZG is a closed subset, irreducible. So it is a prime ideal of OG. Okay? And of course, the intersection on all the different ones is 0. Now, the point here is that first proposition is that IZG is a two-sided ideal in the twisted Hopf. Okay, it is a two-sided ideal. So therefore, we can introduce the quotient algebra. So let me call it OZG, twisted from the two sides. And the theorem, first theorem is that this is an affine Noetherian domain of GK dimension as we like ZG. And in particular, or moreover, it is completely prime, two-sided idea, because it's a domain. So the quotient is a domain. So we want to understand more what happens. So there is a dichotomy here, whether H is, so G is fixed, little g. But H is the support. So it turns out that if H is G invariant, namely this H sub G is just H. So H equals GH, G inverse. So this is the Tukos cycle on the Lie algebra corresponding to the twist, as in our theorem. But at any rate, when H is G invariant, this algebra is nothing but a twisted universal enveloping algebra of H. For example, if G is 1, then as the theorem, this is just, OH, JJ, it's just the universal enveloping algebra of H. So this is generalization of the previous one. Okay, so in particular, a maximal Weil subalgebra has dimension R, where R is the rank of this thing. So for example, if G is 1, of course, there is no Weil subalgebra. R is 0. Okay? Okay, and the other possibility is that H is not G invariant. And this is the main theorem in the paper, which was accepted, by the way, 2 days ago. If H is not G invariant, this algebra contains a Weil subalgebra. And the proof is very long, and but anyway. So I can't say much about it. It's by induction. So the point is that there is nothing canonical here. So therefore, we can now get the following theorem. So every irreducible representation, well, that's another theorem. It's not therefore, sorry. Another theorem is that every irreducible representation, not necessarily finite dimensional, of this algebra factors through a unique quotient. And that's why I introduced the representation theory of these, because once you know that, you can now get the following result. So let NGHJ denote the subgroup of the normalizer of H in G, consisting of all elements such that J is G invariant. So then you get that there is one-to-one correspondence between isomorphism classes of finite dimensional irreducible representations of this Hopf algebra and elements of this group. So the point being, so since every irreducible representation factors through a unique quotient, we know that these quotients have one-dimensional representations if and only if they don't contain a Weil subalgebra, because Weil algebras do not have finite dimensional representations. Okay, so again, so the idea is that every irreducible representation of this Hopf algebra factor through a unique quotient. Now, for these quotients, there is dichotomy. Either they contain Weil subalgebra, or they are simply essentially universal enveloping algebra of the Lie algebra of the support, essentially. And that depends on whether J is G invariant or not. So that can be extended also to describe all finite dimensional representations in the case of connected nilpotent. So yeah, so thank you very much.
Okay, thank you.
So we made it after all.
So are there any questions?
So for solvable groups, everything is open.
For solvable, yeah. For solvable, I don't know if one-sided is simple. I'm pretty sure it is. And probably it's along the line, it's, localizations of Weil algebras, like in the example. So for unipotent, but it's a combination also with those E lambdas which come from tori. So, and you see the problem is that, so let's just maybe quickly, already for two-dimensional solvable, you don't see a clear connection. So this is a minimal Hopf-2 cocycle. Its restriction to any one of these is trivial. So, by the way, yeah, so it's not, I think it's much more complicated to classify Hopf-2 cocycles, to understand. But as I said, even if I knew it was simple, it's not clear. I mean, how to get from it something like in the unipotent case, we could get, this symplectic structure on H. Yeah, and actually one of the questions I forgot to write down, and this is already in a paper with Ettinghoff from 2008. So maybe here I would, this is very interesting. Suppose H is reductive. And suppose J is a minimal Hopf-2 co-cycle for H. H is reductive. Does it imply necessarily that H is a torus? So we expect for good reasons that for reductive groups, the connected component of the support of any Hopf-2 co-cycle has to be a torus. And this would be a key step in the full classification. I mean, if you knew that, and if you knew what happened for solvable, you can somehow, but it's absolutely unclear. So, I mean, in terms of Hopf algebras, I mean, so remember that, so you have the Hopf algebra OH, if H is reductive, is co-semi-simple. And to say that J is minimal, so you have a co-semi-simple Hopf algebra. As an algebra, it's the same. As a coalgebra, it's the same, but different algebra. And it has a non-degenerate Hopf pairing, this form. So why that implies that it is commutative? It has to be a torus. So yeah.
More questions?
I have a question. Yeah. I have a question, Shlomi.
Yeah, sure.
Suppose the group is simple, and there is a correspondence between these two co-cycles and the twist of the universal enveloping algebra, right?
If G is a simple algebraic group, you mean simple Lie algebra?
Yes.
Yeah.
No, there is a duality between O of G, the coordinate algebra of G, and the universal enveloping algebra of the Lie algebra corresponding to G, say SLN. And for the Greenfield constructions, you know the twist on the universal enveloping algebra, or some of them. So if you go back using the duality to the coordinate algebra, you get some two co-cycles. Is that right? So I think you get some of them, but not all of them, or there's some, that's maybe I'm missing something there that you don't get the co-cycles that you want, or you need something else. So what's the key?
Yeah, I mean, it's not clear. I mean, it's not so clear what is the relationship between, Hopf-2 co-cycles, let's say, solutions to the classical Young-Baxter equation, let's say, instead of twists.
Okay.
So Greenfield theory, everything has to, I mean, for the Lie algebra, you look at solutions to the classical Young-Baxter equation, but it's not, I don't see even how to start with something like that and get. I mean, for example, this twist appears in the literature. This is Jordanian twist. So it comes from, it corresponds to some non-degenerate solution to the classical Young-Baxter equation for the Lie algebra. But in terms of it, the expression is very complicated, even in this case. But I'm not sure. I don't know a theorem which tells you anything.
It would be good to have a theorem like that or something related. Yeah.
Okay. I mean, all this quantization machinery, I mean, it was useful in the unipotent case because you could get, from power series, you could get polynomials because unipotent, everything is nilpotent. But if not, then you know something about, in power series, but it's not clear how to go from it.
Okay. Good.
So in fact, let me even say, because that's a good, I mean, in fact, in our paper with Ettinghoff, we recall a result of Drinfeld, which in principle is relatively basic. So if you have a solution, non-degenerate solution to the Young-Baxter for reductive Lie algebra, then this reductive Lie algebra is abelian. So this is kind of what we are expecting, but it's totally unclear how to get it. And you can look, I mean, the proof of Drinfeld is relatively simple. So we need to somehow unlinear it or something. It's not helpful at all when you talk about Hopf-Tuchel cycles for.
Okay, thank you.
Are there non-standard twists of unipotent groups?
No, nilpotent no, because let's say connected. So all irreducible representations are one-dimensional.
Ah, okay, it's solvable.
Yeah, so it must preserve, also for solvable, it's standards. It must preserve the dimension. Non-standard appears when, in the reductive case, for example.
So for SL2, you know the classification of all non-standard, or this is?
Yeah, of all of them, yeah, this is in Bichon. But, and I think there is another paper maybe about SL3. And I'm not sure it's also non-standard, I think standard. But that's it. I mean, the techniques, someone by the name On, O-double-N. And he mentions specifically that, I mean, it's impossible to use these techniques for SL4 already, so that's the only thing I know about, you know, reductive. SL2, SL3, and that's it.
And the standard for SL2 are classified?
Sorry?
The standard ones for SL2.
Yeah. For SL2, I think Bichon classified everything, standard, non-standard. For SL3, I think only standard, I'm not entirely sure. And there is a nice paper, one of the authors is Neshveyev. I don't remember, but together with another one, I forget now. But they classified Hopf-Tuchel cycles for not OG, but in the unitary. So G is a compact Lie group. And they classified, in particular, they proved the conjecture I just mentioned about the support being abelian. But as they mentioned, I mean, they use really functional analysis and operator theory in a very essential way. I mean, it is absolutely unclear how to go from that to the algebraic case. But at least it's a very interesting paper. It's quite complicated, but just remember that all this Tanakian business, I think, started with compact, and then, you know, Deligne. So something big is missing. It would be interesting to.
Yeah, sure. Very interesting. Thank you.
Yeah, thank you very much.
Yeah, very interesting.
Yeah.
So let's thank Shlomo again, and I will stop the recording then.